If you ever tried reading Uniswap documentation or diving into the code, you know how dense it can get with all those structs, actions, and functions flying around. It's easy to feel lost before you even start coding. In this video, covering the essential building blocks you need to understand before jumping into development. I will walk you through core components like structs, liquidity maths, and how to create a profitable liquidity pool, all explained in plain language. Everything we build in the future coding sessions will stand on this ground. Let's break down the pool key struct. It's the blueprint that defines every pool in Uniswap 4. Every pool starts with two tokens or currencies, and in version 4 it requires that the currency with the lower address to be currency 0 and the currency with the higher address to be currency 1. And that's to ensure consistency and prevent duplicate pools that has the same currency but in a reverse order. Next in our struct is pool hooks. Hooks are like plug-in points for developers to build sophisticated features like custom automated market makers with different pricing strategies, or advanced trading features like limit orders or dynamic fee strategies. Speaking about fees, when a liquidity provider creates a pool, it decides how much fee to charge on each trade. This is the liquidity provider fee. This fee is how liquidity providers earn rewards for providing liquidities. Uniswap 4 offers unlimited static fee options or dynamic fees, unlike version 3, which offered only 4 fixed fee tiers. Swappers pay swap fee, which include two parts: liquidity provider fee, which goes to the providers, and the protocol fee, which goes to the Uniswap protocol. Key part of how pools work is tick spacing. Imagine a pool's price is not a smooth line. It moves in small steps, like the tick on a ruler. Each tick is a price point where liquidity is available, and the tick spacing is the distance between those ticks. Why tick spacing matter? Tick spacing determine how precisely prices can be set in a pool. Here is a simplified example of how tick spacings affect your liquidity range. In an Ether USDC pool, let's assume that the initial price of the pool is 1000 USDC for Ether, which means 1 Ether worth 1000 USDC. With tick spacing of 10, the pool will stay in range as the price moves in steps of 10, like 1010, 1020, or down to 990, 980, and so on. If the text spacing is 100, the price range moves in bigger jumps like 1100, 1200, or down to 900 and 800 and so on before the pool reacts. In both cases, the pool only earn fees when the current price is within the pool price range. Pool key struct is a vital struct in all liquidity management operations, and it's all you need to initialize the pool without funding it. But to get a liquidity position up and running, you need to execute two functions in a single transaction using a multi-call. First function to encode is the initialize function from the pool manager contract, and it is to set the pool configuration. And the pool configuration has two parameters: the pool key struct and the starting price. But the starting price has a special function, and it's equal to the floor of the square root of the token 1 divided by token 0 and multiplied by 2 to the power 96. For instance, in an ETH USDC pool, the price of pool is $2,561.80, and the USDC is the stable coin, so it's always $1. Since ETH is the native currency, its address is wrapped by the currency library to address 0, which has the lower value as currency 0 and the USDC as currency 1. The square root of 2,561 and 80 cents divided by 1 is 50. Divide that by 2 to the power 96 and it gives us this huge number on the screen. Please note that some early guides give ETH a special ID since it is the native currency, but in Uniswap final code there are no special treatment for ETH. It is just like any other currency and it gets sorted accordingly. Second function to encode is to modify liquidity's function from the position manager contract with actions as the first function parameter and the parameters as the second function parameter, where each action is represented by a set of parameters respectively. First action to encode is mint position. When you fund the pool for the first time, you have to mint the NFT that represent your liquidity position. Mint position parameters are pool key struct, address receiving the NFT, the HOX data if any, a maximum amount you're willing to provide for both currencies, liquidity units, and last is the upper and the lower ticker, which represent the minimum and the maximum tick spacing. Second action to encode is settle pair, and it is to pay off the two currencies you specify in the pool keystruct. Third action to encode is sweep, which basically sends any excess ether, if any, to the recipient address. It's time to answer the question if ticks go on forever or is there a limit. You need to be extremely cautious when selecting upper and lower ticker to avoid out of range liquidity situation. But what do I mean by this? Well, your upper and lower ticker determines your pool's price range. And let me explain what I mean using the same ETH and USDC pool. When you choose a tick spacing of 10 and your lower ticker is equivalent to $980 and your higher ticker equivalent to $1,020, if in the future the pool price becomes $910, you stop earning fees because the pool price range become above the current price. In other words, the current price dropped below the pool's minimum price. Another case is if you initialize the pool and choose a tax spacing of 100 with lower ticker equivalent to $900 and a higher ticker equivalent to $1,200, and the current price is $1,250. Your liquidity is out of range because the pool price range is below the current price. Out of range liquidity is when the current price falls below your lower ticker or rise above your upper ticker. And it can easily happen because of the swap activities or just because you set a price range above or below the current price. Now let's check out the comprehensive list of all actions categorized by their purpose and functionality. First are the pool liquidity actions. Increase liquidity action is to add liquidity to the pool. Decrease liquidity action is to withdraw liquidity from the pool. Mend position is to fund the pool with the liquidity for the first time and to mend the liquidity position token. Burn position is to burn your NFT liquidity position. Mend position from deltas is to mend a new liquidity position from earned fees. Increase liquidity from deltas is to increase the liquidity pool by crediting earned fees to the liquidity pool. Second is the router management actions. First action is to swap exact in single, where you swap in the exact tokens for exchange of the above the minimum output tokens from a single pool. You take this action when you know exactly the amount of token you're willing to pay for above the minimum of the output tokens. Second action is the opposite, which is the swap exact out single, where you swap in the maximum amount of tokens to get exactly the amount of token you need as an output from a single pool. Third action is the swap exact in, where you swap exactly the amount of token to get above the minimum of the output token from a multiple pools. Last action is the swap exact out, where you swap the maximum input token to get the exact token as an output from a multiple pool. Third category we have is the delta resolution, the settle action where you pay off one token to the pool. Settle pair, where you pay off both token involved in the transaction to the pool. Settle all, where you pay off all token involved in the transaction to the pool. Take is to withdraw one token from the pool. Take pair, where you withdraw both tokens from the pool. Take all, where you withdraw all token involved in the transaction from the pool. Uniswap extended the delta resolution actions by adding three other categories. Sweep is to take any excess ethers if there is a remaining balance left. Close currency is you let the protocol automatically decide either to pay off or to withdraw one token. And last is clear or take, and you basically set a maximum threshold of one token that you consider dust, and that dust will be disregarded to save you gas, and any amount above this threshold is to take. Let's overview a few examples. Increased liquidity action combined with settle pair action is used to increase pool's liquidity by paying both tokens to the pool. Increased liquidity combined with clear or take action is to increase liquidity of one token, and if any remaining balance above the threshold is to be returned to the receiver address. Close currency can be used with increase or decrease liquidity action or both, since it either pays off or withdraws one token. Decreased liquidity action combined with take pair action is used when you want to withdraw your earned fees from the pool instead of crediting fees to the pool to increase liquidity. Increased liquidity action combined with settle action is when you want to fund one token to the pool. It is the remedy providers use when their pool becomes in an out of range liquidity situation to get their pool back in the set price range to earn fees. To iterate, a single sided liquidity occurred when the current price of a pool moves outside of the position set price range. It can also be combined with the decreased liquidity action and take action if you want to withdraw earned fees from the pool. Last but not least is increased liquidity from delta action combined with settle pair or settle all action to credit earned fees to increase pool's liquidity. Uniswap recommends to perform liquidity operations before delta resolving actions to minimize token transfers and leverage flash accounting efficiently. Just vital structs to demonstrate are swap structs. Swap from a single pool are two structs. One is exact input single parameter struct and exact output single parameter struct. First common member is pool key struct. Second common member is 041 with value default to false and should be true if you're swapping token 0 for token 1. Third common member is amount. The only key difference is the amount in exact input struct and the amount out in exact output struct. Fourth common member is amount again, but in the opposite direction of the struct name. Since in exact input struct, its purpose is to swap the exact amount of input token for above the minimum amount of output token, so we expect the minimum amount of output. And on the other side, in the exact output struct, its purpose is to swap maximum input for the exact token output, so we expect to give in the maximum amount of input token. Fifth common member is the Hawks data. If you like the video, don't forget to hit
Hello.
the like
At the
button.
end of
If
our
not, it will all
tutorial, I
make
would
sense in
like
the
to thank
upcoming
you for
coding
joining me
session,
on
so
this
don't
deep
miss it by
dive into
subscribing to
Uniswap
the
4.
channel. If you want to dig
If
in
you
a
found this
specific topic
breakdown
or have a
helpful,
question,
don't
please
forget
drop
to
it in the
like,
comments
subscribe,
section.
and
Thank you
share
all
it with
for
fellow
watching.
builders.